All right. Hello, everyone. Let me get this thing rolling. That's 12 o'clock for me and 3 o'clock for the East Coasters. All right. My name's Andrew Wright. I'm a safety manager here for ECC, currently working out of the Hunters Point project. Today's presentation is on HVAC and mechanical system safety. All right. So the learning objectives I have for you guys are to understand, what these systems are, how they work, and how they're installed, to identify the major HVAC and mechanical hazards, to understand the applicable controls and the safety expectations, to recognize common deficiencies and unsafe conditions during site inspections, improve contractor oversight and hazard mitigation, and then apply like a risk-based approach to HVAC work activities. Some reference and some accident stats reminds us why we do it. Fatal occupational injuries. So HVAC mechanics and refrigeration techs experienced an electrical fatality rate of approximately 0.98 deaths of 100,000 workers, which is significantly higher than the average electrical fatality rate across all occupations. The construction industry accounts for the largest share of workplace electrical fatalities. And HVAC and mechanical workers often perform these tasks, within this high risk environment. Across all occupations, it's no surprise, falls, slips, and trips caused 805 fatal injuries in 2020, making them one of the leading causes of worker deaths. And because HVAC workers frequently work on ladders, as you can see, these people are working on ladders in a very safe manner, as you can see in the pictures on the screen. You can see why people get hurt from ladders and from falls in the HVAC industry. All right, some references. I'm not going to go through all of them, but the takeaway here is whether you're under a site governed by the OSHA in 1926, or on this next slide, like the EM 385, there's a lot of regulations and chapters that apply to HVAC work, and the reason for that is there's a lot of different trades and hazards and work processes involved in HVAC and mechanical work. So there's it's a pretty big topic. We're not going to go over everything about HVAC and mechanical, but hopefully by the end of this you'll kind of have a basic understanding of these systems and be able to better do your job if you got some HVAC work coming up in the pipeline. All right, definition. So what is HVAC? Because I'm going to say that acronym a lot, so I should probably explain what it means. HVAC means heating, ventilation, and air conditioning. HVAC work focuses specifically on systems that control a building's indoor environment. These include, your air conditioning units, furnaces, and heaters, heat pumps, ductwork, ventilation system, air filtration systems, building temperature, and and humidity controls. Mechanical work, is a broader category that often includes HVAC work, but also covers many other building systems such as the HVAC systems, the plumbing, process piping, pumps, boilers, chillers, compressed air systems, refrigeration, industrial mechanical equipment. So in commercial and industrial construction, a mechanical contractor may install and maintain these systems, while an HVAC contractor will focus primarily on heating, cooling, and ventilation. So we're going to focus primarily on the HVAC work, but there will be some mechanical work put in there. So basically all HVAC work is considered mechanical work, but not all mechanical work is considered HVAC. That makes sense. So, all right. So I'm a big believer in you have to actually know, what you're looking at and kind of understand the systems that are, being installed or worked on to be, effective at your job as a safety professional. So there's some terms I'm going to throw out there, and forgive me if you already know what these are, but it's important that you kind of understand what they are, just so you understand what they do and what could actually hurt you. So A compressor is essentially a refrigerant pump. It's it's how the refrigerant gets compressed and can release heat. Basically, it circulates refrigerant, and what could hurt you there is pressure, electrical, hot surfaces. Then you have the condenser, which is basically your outdoor heat exchanger. Those are the things that you'll see outside of your homes if you live in an area that has air conditioning. What that does is it rejects heat. It's got sharp fin blades on it. Then you have your evaporator coil. That's your indoor heat exchanger. That absorbs the heat. That's what you find inside your home. Supply duct is very easy. It's the duct carrying conditioned air to the rooms, while a return duct is the duct returning from occupied spaces. So a capacitor. These are the things that go out on your AC unit when it's 110 degrees, and the HVAC technician charges you $1,000 to replace it when it's like a $10 part. But these things, they have like a unique hazard on them, is that they can actually store electrical energy in them. That's what they are. So even if it's disconnected, it could have potential energy stored in it. Contactors, those are just essentially electrical switches. They energize motors, so you got your shock hazards. Your blower, which is essentially the fan that circulates the air through the system. Heat exchanger is a metal heating chamber that transfers heat. It could leak carbon monoxide on furnaces. You'll hear mechanical contractors say something about line sets. What they mean by that is usually the copper refrigerant tubing. This is what is connecting these units and moving the refrigerant around. Your condensate drain. This is the water drainage, because if you're conditioning air, you're often removing the moisture out of the air. That moisture has to go somewhere. Where does it go? The condensate drain line. Okay. All right. Now that we got some background definitions, let's get into some of the common systems and how they move heat. But all HVAC systems operate on the same fundamental principle. They move heat from one location to another. So my goal is by introducing you to these systems and how they work, it'll give you the context you need to be more effective during install activities and kind of understand where the hazards may come up when you're observing the work. All right, so split systems, residential and light commercial. What is it? A split system is the most common HVAC system in North America. It's called a split system because the major components are divided between an outdoor unit and an indoor unit. So, your outdoor unit is the condenser, then inside you got your evaporators. The system transfers heat rather than creating cold air. So refrigerant absorbs heat from outside the building and transports it to the outdoor condenser, where the heat is rejected to the atmosphere. During heating, heat pump systems, the refrigerant flows in reverse and heat is extracted from outdoor and delivered indoors. All right. Continued split systems. Major components you'll see is outdoor unit. You'll see your compressor, your condenser fan or fan motor. The electrical compartment, that's where your capacitors and your voltage coming in works. And then you have your service valves, where you can recharge the refrigerant or check the pressure. Your indoor unit, this is your furnace or air handler. You're going to have your evaporator coil, your blower motor, your air filter, and your condensate drains, and whatever ventilation is associated with that. Connecting components, so you got your copper refrigerant line set, your low voltage thermostat wiring, which is 24 volts typically. Your electrical circuit power, this is the power from your home, which is it's either going to be like 120 or 240 residential, and then it can go up to like 3-phase commercial at various voltages depending on what the application is, and your condensate drain. All right, split systems continued. This is a little bit different system called a ductless mini split. People just call them mini splits. A ductless mini split works exactly like a conventional split system, but does not use ductwork. Instead, each indoor unit conditions a specific room or zone. So basically, one outdoor condensing unit can serve one or multiple units. Refrigerant is circulated directly to each indoor evaporator. So because conditioned air is delivered directly into the room, mini splits are really efficient because they don't have ducts, going through your house. And anytime you have ducting or anything like that, you're going to lose some heat and some pressure due to air loss and leakage. Is just basic thermodynamics. So they are a really good option, for certain applications. And the components of a mini split is, you got your outdoor condenser, your refrigerant lines, and then your indoor wall or ceiling or floor cassettes. This is basically where the air comes from, the cold air or the hot air comes from. All right, those of you who live where it's cold probably are aware of what a furnace is, or forced air heating. So a gas furnace is a forced air heating appliance that burns natural gas or propane to produce heat. So unlike a heat pump, a gas furnace does not move heat using refrigerant. Instead, it creates heat through combustion. The burner ignites natural gas or propane inside a sealed chamber. The hot gas passes through a heat exchanger, and then the fan just blows it through your system. So the combustion gases are vented outdoors through a flue, while the warmed air is distributed through the building. Furnaces continued. Major components is you got your gas components like your gas shutoff valve, earthquake valve if it's required. It's required out here in California. That's that red thing on the in the picture in the middle. Regulators, your gas connector, flux gas connectors where it's permitted, your burners, and your ignition system. And the heat transfer components, you got your heat exchange, blower motor, and then your supply plenum and return plenum. That's just basically where the fan is mounted and starts pushing up the air from. And then you got your venting fan and flue. A note is many homes pair the gas furnace with a split system air conditioner. So a lot of times you'll have your gas furnace and your AC, air conditioner in there too, because it saves space. So you could have your, the same blower, blow cold air or hot air. It's very common. In this configuration, the furnace provides heat during the cold, and the evaporator installed above the furnace is how you get your cold air. Side note, if you're ever, mowing your grass and you hit your earthquake valve and your gas shuts off, these earthquake valves have like a little ball that will fall on a switch and like turn off the valve, and your gas will shut off. This is simulating an earthquake, so your gas will automatically turn off, and you could take a screwdriver and just reset it to save you money and time. All right, forced air heating, heat pump. It's uses the same basic refrigeration cycle as an air conditioner, but it essentially reverses the flow of refrigerant. So it doesn't create heat; it pulls the heat from outside. They work okay, but if it gets really really cold, they're not going to work that well. Hold on a second. Yeah, so even cold outdoor air contains heat energy, but if it's really really cold, the less efficient it is. Um, and they have the same components as split systems. All right, packaged rooftop units, RTUs. What is it? So unlike a split system, all in a RTU, all HVAC components are contained in one weatherproof cabinet. It's usually mounted on the roof. So basically, air is pulled into the rooftop unit, conditioned, and pushed down through the ductwork of the building. Side note: if you're going to have a roof RTU installed, you got to have a roof curb installed. Typically, your roofing contractor needs to do that. So RTUs, the heating may be provided by electric, natural gas, heat pumps, hot water coils. It doesn't really matter. It's just the significance of the RTU is it's on the roof and it's a packaged unit, right? And it has the same components as other HVAC units, compressor coils, condenser. It's just a larger version. One thing that it may be different is it has a lot of them has something called an economizer, which is set up dampers and sensors that controls. It like uses the cool air outside to naturally cool the building, so it uses the free cooling air to allow like ambient cold air into the system, so that you're not always having to run your expensive compressors and everything. Chilled water systems. I call them chillers. What is it? It's a large On large commercial buildings, often don't use refrigerant to cool every room directly. Instead, they use said a central chiller will cool water to like 42 to 45 degrees. The chilled water is pumped throughout the building to air handling units, where it absorbs heat from the building air. The warmed water returns to the chiller to be cooled again, creating a continuous loop. For water-cooled chillers, a separate condenser water loop projects heat through a cooling tower. Components of a chiller is you have your cooling tower, your pumps, expansion tanks, air handlers, VAV boxes, which is your zone airflow controls. It basically tells it directs water from the chiller into certain areas, so that you could, if one room's too cold or one room's too hot, you could adjust it essentially. And control valves. Next, we got your boiler and hydronic heating. What is a boiler? A boiler heats water rather than air. Hot water is circulated through piping to air handler unit, heating coils, unit heaters, radiant floor systems, baseboard heaters, those old school, what do they call them? I'm blanking on it. But basically like a hot water heater that goes through pipes throughout your house. But the cooled water returns to the boiler where it's reheated. Steam boilers operate similarly, but they use steam instead of hot water. Hydronic heating is a very energy efficient way for heating your home, by the way. So that's why they use it in large commercial buildings too, and just supply hot water throughout buildings, because they can provide hot water for showering and heat. All right, components, you got your boilers, your circulation pumps, expansion tanks, heat transfer, gas lines, flue relief valves, same components. Most of these systems share similar components, but they'll maybe have a couple different things in them. All right. Lastly, you have a variable refrigerant flow systems. These are a little, they operate on the same fundamentals. A VRF system is a advanced refrigerant-based HVAC system capable of serving dozens or even hundreds of indoor units from one or more outdoor units. So unlike traditional split systems, a VRF system continuously varies the amount of refrigerant set to each indoor unit based on demand. So you could cool one room and keep while heating another room simultaneously. It's pretty sophisticated system that's very efficient. You'll see it in like large office buildings or hospitals or other multi occupied spaces like that. So it's something that you might come up with. I know I've encountered it several times. All right, summary. So all HVAC systems operate on the same principle. They move heat from one place to another, and all the systems I just talked about are just basically different ways of doing that, depending on the application and the need. So again, split systems move heat with refrigerant between indoor and outdoor. Mini splits do the same without ductwork. Package rooftop units are RTUs, the same thing, but they're on the roof in one package. Your chilled water systems use the water for heat transfer instead of refrigerant, and your boiler systems use your hot water or your steam for the heating. And your VRF is basically the same thing, but it's able to vary itself to multiple indoor areas for precise zone control. All right. Now that we got that out of the way, hopefully you guys have a basic understanding of some of these systems. Let's get into the hazards of the work that you may encounter. All right. Number one, falls from heights. So, they always say falls is the leading cause of, deaths and catastrophic injuries on job sites. It's no different in the HVAC field. Rooftop units, curb install, elevated ductwork, access from ladders or scissor lifts or aerial lifts, whatever, cooling towers, mezzanines from, if there's a elevated area from within a big industrial building, you'll see those a lot, especially when they, have all the duct work suspended from the ceiling. They'll often have their, air handlers and stuff suspended from the ceiling in a mezzanine. Those are areas where you have to think about fall protection and skylights, if you're working on a roof. So your controls are similar to your roofing controls or any other working at heights, guardrails, warning lines, covers for skylights, fall protection systems, your fall protection plans, ladder safety, all that stuff. Field observations, if people are working near roof edges or unprotected sides of mezzanines, improper anchorages, so HVAC guys, they're typically not, if they even have fall protection or have even worn a harness, a lot of the times they're not going to have the knowledge to, use fall protection systems properly. So it's up to you to make sure that we plan these tasks out way in advance so that, you're not just having some HVAC guys just show up and expect to, get up on a roof or, start working out of aerial lifts without, the proper planning. And misuse of ladders is something that we see often. All right, electrical hazards. All these systems, one way or the other, run off of electricity and have some sort of electrical component. So your condensers, your RTUs, air handlers, furnaces, chillers, your controls, all have, typical voltage and exposure points. When you open up a panel, to add a new line for a HVAC system or a disconnect switch, all those times you have, exposure to, electricity. So you got to make sure that you and your workers are, competent in the electrical safety aspect. So some high risk electrical components are going to be your disconnect switches. Those are the the levers that you'll see pretty close to where these machines are, the HVAC systems are. Capacitors can retain a dangerous electrical charge even after power is removed. Contactors, that's where you have your exposed electrical terminals. This is where your HVAC techs are going to want to open up a system and to troubleshoot it. It has to be on, so they're going to want to make sure that you have they're wearing their proper PPE, like arc flash PPE and stuff like that. If they have to work on energized systems, and there's actually like energized work permits and stuff like that if you have to work on live panels and stuff like that. Electric heat strips, those are high voltage energized heating elements that are in ducts that they basically get really hot like a hairdryer, and they blow air over to create heat. Those are usually what you see like in systems like emergency heating. They'll have like the heat strips in there. Fan motors and compressors, unexpected startup and rotating equipment. So takeaway is the greatest electrical hazards occur during startup, troubleshooting, testing, and maintenance, not just install. Install has like the least amount of electrical hazards because you haven't energized anything yet. It's usually when you're out there troubleshooting or doing maintenance that these electrical hazards are the most prevalent. All right, so electrical, before work begins, make sure your qualified workers are performing, the electrical tasks. Make sure you're implementing lockout, tagout as needed, and we'll get into that more. Test before touch, which basically means contact testing the switches and terminals, making sure that they are in fact off before you start touching them. Proper electrical PPE like arc flash PPE, your gloves and your suits and your masks as needed. The correct meter and insulated tools being used. The equipment disconnect identified and accessible. So what are some stop work conditions that may come up if you're like a SSHO? You go up to a system and you see that they got the electrical panel open on a HVAC unit, and you go to where the main panel is, and you see that it has no lock on it, that it's on or maybe it's off, and they didn't put a lock on it. That's a stop work. Worker contacting energized components without permission or justification. Contact capacitor or VFD service without controlling stored energy. VFD means a variable frequency drive. It's a motor controller that changes the speed of the motor, essentially. Open energized panel left unattended. So if you pull the face off a panel, or like in the picture in the middle, if you just leave that open and it's hot, don't do that. Damaged cords, missing covers, bypass electrical safety devices, unqualified personnel performing troubleshooting, that sort of stuff. All right, hazardous energy control, or LOTO, lockout, tagout. HVAC equipment often contains multiple hazardous energy sources beyond electricity. So what are they? Electrical is the obvious one, your motors, your controls. You also have mechanical, fans, belts, dampers. You have the potential for caught-in and amputations. I know at my last job, they sent in some training tech into a big industrial air handler while it was running, and her ponytail got caught in a fan motor pulley, and it removed her ponytail. Not to get too graphic, but so it's very important that you're making sure these systems are off, especially with mechanical injury, because it will keep moving with you in there or without. Pneumatic, this is air. Pneumatic is air, so actuators, controls, hydraulic, equipment lifts, crush injuries, refrigerant pressure. These compressors and line sets are under pressure, so if unexpected refrigerant leaks, it could cause frostbite or hose whipping or injection injuries. Natural gas, if you're working on boilers or furnaces, obviously the injury is fire, explosion, and then steam. For boilers is going to be your burns, right? LOTO continued, so let's make sure we got energy that needs to be controlled, that we're identifying all the potential sources. We have equipment-specific procedure that is signed, zero energy verification. Real quick side note, even if you call out the boss contractor or utility owner and they say, yeah, everything's good, it's the gas line is off or whatever is off, verify yourself, because I had this happen to me when they told us like, oh yeah, the gas is off, we turned it off, and they opened up the bleed valve to let the system drain out, and it just kept going and going and going. What had happened is they turned off the wrong gas system, so my gas lines were still energized, and we were going to do work on it. So I had to get them back out there and basically say, no, you guys messed up. You guys didn't cut off the right system. So make sure you're actually double checking it yourself, especially when there's a lot to lose on the line. Stored energy release, capacitors, pressure springs, that sort of stuff. Locks tag, applied by each worker. So if you got multiple trades, add a hasp on there and have multiple locks on there. And then your test before touch. So when will we stop work? No energy verification, multiple energy sources not isolated, a shared group lock, a shared lock without a LOTO, guards removed on energized equipment, and equipment restarted before the lock is removed. All right, chemical exposure. There are chemicals that are used in the HVAC world. So most obviously, you have your refrigerants. Either you'll get them when people are charging them or recovering them. They could cause frostbite if they get on your hands or your skin. And if you're in a confined space, they could displace the oxygen and be an asphyxiant. If you're brazing or soldering, you got your fumes from welding. You got your silica dust. A lot of times when you're running line sets, they have to core drill or install concrete anchors. So if you're doing any of that, you got to have your silica control plan because the risk of silicosis is real. If you're doing maintenance, they have coil cleaners, and these are usually very basic or caustic chemicals that they use to clean the the coils or whatever to remove scale or whatever, and they're pretty nasty chemicals a lot of times, and they could cause very severe eye damage and skin damage. And then your regular adhesives and cleaners. And as a side note, make sure that your subs aren't bringing any like weird solvents onto the job site because the EM 385 doesn't let you use like certain solvents, like MEK or whatever. You're going to verify that the SDS is available and followed, that proper refrigerant recovery equipment is in place, that your cylinders are secured. So a lot of times I see these workers, they have these their tanks and they just let them roll around on the ground. So make sure that they're secured with the caps on. Dust control, vacuum, wet methods for silica, ventilation, and then your proper PPE. All right. Fire and hot work. So typical HVAC hot work is going to be your brazing and soldering copper, welding supports, cutting steel with a chop saw or grinder, some torch work. A lot of times you use propane, oxyacetylene, MAP gas, whatever, and then grinding metal. So those are your hot work activities. Make sure you got a hot work permit and the fire prevention stuff that goes with it. So fire hazards, maybe from insulation, wood framing, roofing materials, dust, combustible storage, gas cylinders, what have you. Just make sure you're following all the hot work procedures on the permit. If you got gas welding going on or gas brazing, make sure they got flashback arresters. It's an adequate ventilation. The gas cylinders are secured. They're not going to tip. And they got the proper PPE, for the hot work, welding gloves and the proper shaded eye protection. All right, pressurized systems. Common pressurized systems is going to be your refrigerant piping, your nitrogen pressure testing for purging, boilers, hydronic piping, air compressors, pneumatic controls. Hazards is, hose whip, flying fittings.
Sorry.
Hey, can someone go on mute, please? Thank you. All right, hazards, hose whip, flying fittings, overpressurization, sudden pressure release, refrigerant release, fluid injection. You got high pressure hose lines and connections that, they don't cope well with, exposure to skin, anything like that. Pressurized cylinders, as you can see in the picture here, there's some cylinders not being stored correctly. I don't know if that's oxygen or whatever, but they use cylinders for pressure testing, brazing, refrigerant recovery, and charging the systems. So you got your high pressure release and hose whips, projectile hazards from a broken valve. So like if a pressurized cylinder falls and the valve stem breaks off, that cylinder basically turns into a missile. So you got to make sure that that's not that's secured at all times, one way or the other. Frostbite from rapid gas relief, oxygen displacement in enclosed spaces if they're using CO2 or nitrogen, cylinder rupture due to heat exposure, and then flashback during brazing. Safety controls are securing cylinders with a chain, making sure they're stored properly with a fire barrier in between them. Valve caps on cylinders, using the correct regulator or making sure it's not damaged, keeping oxygen separated from fuel cylinders or separated by a fire barrier, transporting them in carts, never dragging, rolling, or lifting them by the valve, protecting cylinders from heat, sparks, or damage, checking the hoses, regulators, and everything like that, and then, making sure everything's turned off before you leave. So. All right, confined spaces. Sometimes HVAC guys might have to go into confined spaces. These may be crawl spaces in certain criteria if they meet the criteria for a confined space. Um, Mechanical vaults, utility tunnels, air plenums, tank interiors, equipment pits, vaults, what have you. The hazards there in confined spaces, oxygen deficiency, toxic atmosphere, heat stress, restricted egress, engulfment, electrical hazards, and biological hazards. So you're going to verify that the space has been evaluated, their atmospheric testing and ventilation is complete. Issue a permit if required, and make sure the permit is followed. Make sure they got a rescue plan if required. Make sure they got an attendant, and make sure you guys have good communication. All right. Biological hazards. So HVAC technicians routinely access equipment that's been, undisturbed for months or years, exposing them to biological hazards that can cause, bites, stings, allergic reactions, respiratory illness, or infections. So there may be spiders or insects in the mechanical rooms, attics, wherever. Bird nests and rodents, air handlers. It can be found in air handlers, ductwork, wherever. You can get diseases from rodents and birds. Side note, if you're ever, in the Southwest in warm, dry climates and you are opening a mechanical room for the first time, it'd be better to open it and let it vent out, because if there's mice droppings, you can get something called hantavirus from like the aerosolization of like rodent droppings, and hantavirus is extremely bad to get. You'll probably die if you get it. So don't dry sweep or vacuum in those areas. Make sure you're airing it out. Wash. You could soak everything with some mist or some bleach, something like that. Just a side note there. Mold and mildew, very common in the South. In these in the fan coils, on the air blowers, in the drain pans. People have different tolerances to mold. Some people doesn't affect very much, like me, and then some people it really messes them up and trigger, asthma or whatever. So that's something to look out for. Legionella bacteria. This is found in it can be found in cooling towers or evaporative condensers or stagnant water. HVAC workers have a risk of getting Legionnaire disease when they're servicing the equipment that has, with stagnant water, found in like cooling towers or evaporative condensers. And so make sure you're taking the proper precautions, and are addressing this hazard. And then we talked about the animal waste hazards, hantavirus, histoplasmosis, salmonella, that kind of stuff. Carbon monoxide poisoning, the silent killer. Common sources are gas furnaces, boilers, generators, heaters, any combustion equipment. It's caused by poor combustion, it could have a blocked flue in your or vent pipe in your home furnace, in a cracked heat exchanger, found in furnaces, boilers, generators, whatever. If you got any type of combustion going on in your home for heating air or your water heater, make sure your carbon monoxide detector is working and test it out every now and then, because it's very tragic when entire families can get wiped out through carbon monoxide through something as simple as your furnace is got a leak and it leaks all night or whatever, or maybe the pilot light goes off and it's just basically putting anyway, it could cause a lot of harm and be life threatening. It can't be seen, can't be smelled, can't be heard. So it's starts with a headache, and then heart rate increases, you get tired, your breathing gets difficult, impaired judgment, and then eventually you get a really bad headache or you go to sleep. and you never wake up. So make sure you're taking that one seriously. Material handling. So when you guys are installing new systems or replacing, components, you're going to have to handle some material, and that comes with its own hazards, right? So that's your forklifts. You're going to use forklifts, telehandlers, a crane if it's a large rooftop unit or something like that, a gantry crane, which is the picture in the middle to the right, maybe a duct jack, which is the picture on the far left. These are all means for installing and handling the equipment. So your hazards are typical with most material handling jobs. It's overexertion if you're picking up stuff by hand, pinch points and struck by if you're using equipment, load handling equipment, suspended loads, sharp edges, improper rigging, and falls from heights. So as the SSHO, verify that if you're using rigging or cranes or anything, make sure you got a lift plan. Make sure your rigging is inspected, your operators are, qualified. The load is secure, the travel path is clear, and then team lifting on, stuff that's on the ground and, wearing gloves and other PPE, to protect your hands if you're handling material. So you should always opt for mechanical means of, installing, the actual equipment or the ducting or anything like that, because a lot of contractors, they're not going to want to spend the money to go get a duct lift jack. They're going to be balancing up on ladders or something to install duct work. It's really better if they have that equipment there. It's safer for them and it's more efficient. So you could definitely make that case for them to like, hey, you guys are going to get the right equipment out here to do it safely. So those are fights often worth fighting with subcontractors, make sure that they spend a little extra money to get the job done safely. Germicidal lights. So these are UVC lights. Typically are installed in air handlers, ductwork, and rooftop units. They disinfect coils and they reduce microbial growth. They appear faint and blue. They don't initially hurt your eyes to look at because UVC is, it's not really in the visible light spectrum. So it's not like looking at the sun where it's very bright and you'll look away. You can look right at these things. So you may not know if there's not a warning sign at it that you can't look at these. And I actually know somebody who was installing one of these in his house, and he ended up looking at it for maybe 2 minutes, and then about 8 hours later, he wakes up in the middle of the night, and his eyes basically feel like they're on fire because he got flash burn from the UVC. So it's very important to know what these are. Don't look at them. Make sure they're locked out if you got to change them. People think, oh, UV light, I could just wear sunglasses. Not the case. UV, like sunglasses that you buy from the store, are UVA and UVB spectrum. They will not stop UVC because UVC light typically comes from the ozone. It's typically blocked by the ozone layer. So our sunglasses don't block for that. You have to get specific lenses, specific goggles that block UVC light if you're going to mess with these lights when they're on. And it can also burn your skin, but the worst thing is getting flash burn because if you've never had it, it's awful. So yeah, make sure if you're going to be working with these, make sure they got the light has a warning label. Don't interfere with door interlocks. A lot of times these things are in interlock systems and you can't really get to them. But if you do got to do it, now you know about them. All right. Building automation systems and remote startup. I'm bringing this up because a lot of like modern commercial systems can be remotely energized from a building automation system. So a tech may assume equipment is off and safe because it's locally turned off, but the backup power or automatic restart features can create hazards. HVAC systems are also tied into the system, can also be tied into the building's life safety system. So a lot of times they'll have like duct smoke detectors, that will trigger if there's a fire, and they'll automatically, shut all the dampers so that they're not pumping smoke throughout the room or, throughout the building. And if you're working on one of those and you set it off, the fire department will come, which I have learned firsthand. So it's very important that, if you're working on a system that is tied into the life safety system, that if you're going to be working on it, that you put the system in test mode so that you're not going to get the fire department showing up at your job site, because they're usually not happy about that. If you have a automation system, make sure that's included in the lotto procedures, and whoever is operating that system, if someone is included in that and is aware that what's going on. Yeah. All right. Summary of high risk activities. So we reviewed, the specific hazards and some other high risk activities, cranes, obviously roof work, electrical startup, refrigerant charging, brazing, hot work, pressure testing, mechanical rooms. This is there because this is a place where there's usually multiple trades in there, and multiple systems going on, and heavy equipment placement. These are like the kind of the higher risk, higher loss potential hazards that you could look at first when you get to a job site. All right, trade coordination and deconfliction, SIMOPS, which basically means simultaneous operations. All right. So why does coordination matters? It matters because HVAC work rarely occurs in isolation. Mechanical contractors often share work areas with electricians, plumbers, sprinkler fitters, roofers, drywall installers, control technician, tab contractors, which means testing and balancing, crane operators, and commissioning teams. And a lot of serious incidents occur because one trade creates a hazard that another trade is not aware of. So it's really important that we deconflict these trades as needed, So there may be HVAC activity as like a crane setting an RTU on a roof. Brazing refrigerant piping may expose, insulation guys or painters to hazards. Pressure testing may affect other guys working in the mechanical room. Electrical startup, can affect the controls, the tab guys or the electricians. Core drilling, can affect electricians and plumbers. Duct insulation can affect other workers. Refrigerant charging and can affect occupied areas, and then roof work. And you also want to coordinate, if you're working in occupied buildings, it's also very important that you're coordinating between the occupants as well. All right. So before a task begins, it's important to ask, to deconflict these trades is who's working the area today? Will today's activities introduce new hazards for another trade? Have you had your daily coordination meeting, your tailgate meeting with all the trades? Are they aware? Has everyone been read in on what's going on at the job site? Are exclusion zones established and communicated? Does today's work require sequencing or temporary work restrictions? Have changes to the work plan been communicated to all workers? So high risk, I'm not going to go over it again, but there are, high risk simultaneous operations that are going to require a little bit more work. Anytime you're setting equipment, hot work, electrical startup and energization, pressure testing. If you got multiple aerial lifts, or scissor lifts working in an area, anything with confined space and multiple trades, anything with roof work and commissioning too, because on commissioning days, it's usually kind of hectic and there's a lot of different trades going on in there, getting this equipment up and running. Mechanical rooms, most huge industrial buildings or, barracks or whatever have a mechanical room. There's potential simultaneous hazards, panels going on in there, boilers, gas piping, refrigerants, potential for confined spaces, poor ventilation, noise, hot surfaces, rotating equipment, multiple contractors in there, carbon monoxide. So mechanical rooms are, need special emphasis when you got a lot going on in there. It's not like your typical, work environment. There's a lot of moving parts and different things in there that everyone should be aware of. Um, sequencing is really important. So a summary of a typical work sequence, that I would do like on an HVAC job is I'd plan it first, get the AHAs, the hot work permits, lift plans, material staging, exclusion zone set up, make sure that's all dialed in. Equipment placement. So it's when you're doing new construction, how is the equipment going to get installed? Are they going to use a crane, a forklift? Is there going to be rigging, gantry cranes, duct lifts, what have you? How is the equipment going to be, installed once it's set? Setting AHUs, furnaces. This is then how is the mechanical stuff going to be installed? That's your ducting, your piping, refrigerant lines, gas piping. Then installing electrical and controls. This is your disconnects, your wiring, your controls. System completion, your installation of your duct, labeling and sealing everything. Then lastly, you got your testing and commissioning. You're going to have, pressure testing, balancing, all that stuff. And then you're pretty much done after that. All right, so our oversight responsibilities, pre-planning, reviewing APPs, vetting our subs, either making or, reviewing AHAs, lift plans, confined space permits, verifying that the subs understand the site-specific work, hazard recognition, anticipate hazards before work begins, identify changes into sites and conditions, and identifying SIMOPS, field oversight, conducting frequent observations during high-risk activities, verifying that the controls remain effective throughout the shift, not just at the morning briefing, exercising stop work authority when imminent danger exists, and ensuring the work resumes only after the hazards have been, corrected. So it's always helpful, to ask yourself, what could go wrong next? What's changed since the morning? What assumptions is the crew making? Or are they assuming that the lotto is still in place? Is it still off? If something fails, who's going to get hurt first? And what is the worst, credible outcome that could happen? What if everything goes wrong? What could possibly happen? Okay. All right. So final takeaways from this presentation is, I hope that you can understand the fundamentals of the systems you're working with. You could understand each job step and the associated hazards that'll allow you to, think ahead. Focus on the high loss potential hazards first. Verifying controls in the fields, not just on paper. Coordination across trades and deconflict as necessary, and then using your stop work authority, because it's easier to prevent an incident than investigate one. It's a lot of paperwork. All right. Any questions?
I have one.
Yes.
First, I'd like to apologize for my interruption earlier, but my question is regarding a heating system in your home. What's the safest in terms of age one should have in their home? Like, is it 15-year-old? Is that still a good system to keep, or it
I
should
honestly
be
don't know.
one?
I honestly don't know. It would probably depend on, how it's installed and, if it's working properly, but I don't really know. That seems like something that it may work fine because I know that there's, HVAC systems from like the 70s and 80s that still work perfectly fine. So it may be a safety hazard. I don't know, but depends on who's telling you. If it's like a HVAC guy trying to sell you a new system, it might be worth looking into. But I honestly couldn't give you a blanket answer for like 15 years is too old. I don't know. So sorry.
That's okay. Thank you.
Yeah, no problem. Anybody else? All right. Thanks, everybody. Appreciate it. Have a great day. Bye.
Make sure everybody
Thanks all.
does your
Thanks.
quiz.
Yeah.
That way